Yeah, thank you very much. Thank you for the invitation. It's a great pleasure to be here and share a little bit what we are doing in the Animal and Dairy Science Department. It doesn't sound always that we do that type of work in animal science departments, but that's an area that is growing a lot: precision agriculture, digital agriculture, precision livestock. And I'm assistant professor there, working dedicated in precision livestock farming and technologies to automate phenotype collection. So that's what we are doing there. And computer vision is a big component of the applications that we are deploying and testing to collect such phenotypes. Okay. So I will go quickly and do a briefly introduction about why we are doing this, why using computer vision, why we are collecting that animal level phenotype. The majority of the work that we are doing is trying to develop ways to have high throughput phenotyping systems, thinking about animal level information. Okay, and the reason of that is that by having detailed information about the animal, we can have at the farm optimized decisions about what to do with this animal related to health, nutrition, reproduction, and genetics, which is a big component of this phenotyping, precision phenotyping, or the need of large scale phenotyping collection. We have in precision agriculture, people collecting data from different sources. That is very advanced in crops. So we see people integrating data from crop, from weather, soil, water. In livestock, one missing point is the animal level information. We can aggregate data from public database, data from farm, but we do not have a way to have animal level information, or we have very few sources of animal level information. And this limits us a lot what we can do in terms of optimized decisions. Okay, so when I talk about animal level information, I'm talking about animal identification, behavior, body weight, milk component, feed intake, all things that are expensive or are time consuming to be collected. So large scale operation, 30,000 animals, 20,000 animals, 10,000 animals, it's almost impossible to collect if you do not have sensing technology. So we have sensors to collect these. We can use wearable sensors. We can use infrared spectroscopy, sound systems, and different types of sensors. One of those that we are using that are very promising is the cameras. And so several of the applications that we are developing in the lab are related to machine vision or to computer vision applications. Okay? And that's why we are using HTCondor and collaborating with HTC is that we do not have the infrastructure to do this, especially considering the size of the data sets that are getting bigger and bigger that we're collecting, so we cannot handle that in our lab. So without HTC, HTCondor would be impossible to handle those analyses. And I will give some examples, okay? So that at the end, we want to have a cheap, precise, and real-time phenotype, and that's what we are working every day to have and to be implementing in livestock operations. Why computer vision? Are you gonna probably see that easily? Is that if you work with other technologies as wearable sensors, let's say you're gonna put accelerometer in a cow and you wanna measure if the cow is grazing and not grazing, we can clearly capture a signal of the accelerometer, of the motion of that cow, and we can train an algorithm to classify if the cow is grazing or not grazing, okay? But this is limited for that specific phenotype. And without the label of grazing and non-grazing for that G-force or for that accelerometer, I cannot tell other things that are happening in this environment of this cow. When you think about collecting an image of a cow, okay, I can predict based on that image if this cow is grazing or non-grazing, but also I can have information that is rich related to things that I'm not even considering at the first moment, right? So I can tell, for example, if the breed of the cow, if it's a Holstein cow, if it's a Jersey cow, or the condition of the pasture, if it's green, if it's not green, if it's dry, if it was raining that day or not. So there are several information that we can extract. We can count the number of animals. So there are several things that we can do with the image. So that type of data source is very rich. And then we are very interested, not only for the short term, but for the long term thing in the future, as we collect that data, the possibilities that we could have to work with that type of systems. Okay, so that's why we're doing most of the work related to computer vision. We're using deep learning as our main framework in different type of tasks. For image analysis, that's been the state of the art in terms of classifications and detection. So we are using this and successfully have good predictions, implementing that type of approach, analytical approach. And we are doing simple analysis classification of image, saying there is an animal there is no animal there is feed, there is no feed on the bank, through segmentation and segmenting the animal, getting the body shape, and using the shape, the 3D shape for image classification and running classifying 3D deep learning models, algorithms, and using for detection and detect animal in different locations of the pen, in different situations at the farm, through image synthesis. We are not doing a lot here, but we see opportunities of augmenting some of the data sets that we have and generating image of cows that we need and we do not have in our database. So running these in local computers or running these in our lab, it's almost impossible, considering the size of the data sets and the number of parameters that each deep learning algorithm has its own. Okay. What do you want to do? Our vision is that we want to do as other domains are doing in terms of tracking and monitoring as autonomous cars, or smart cities. We want to track animal behavior, animal locomotion, and then study how these affect welfare of the animal, how we can select efficient animals, how we can early detect a health issue in animals, how this is related to social interaction of animals, and this could be done through computer vision. So that's our goal in the lab, is to develop systems like this. So here's an example, 3 examples of baby calves, heifers, and cows, which are tracking specific behavior of those animals, if they're drinking milk, if they're standing, how frequent they are visiting the feed bank, how long they're staying in the feed bank, and then by putting this information together in a large scale, we can monitor every second or every 5 seconds of a cow activity in a day, and based on that, we can hopefully have optimized decisions if we're able to collect the data, run inference, and have that in the time that we need, time window that we need. Okay, we can go further and do more detailed behavior. That's something we are doing and investigating at the cow level, not only if the cow is eating or not, but how the cow is eating. So I have kids here, and when they see the greens, they have more hand motion because they try to select what they want to eat. And that's the same with cows, except they do this with the mouth. So they try to select for more for large particles, or some cows for a small particle. It depends on the diet. And if the cow is selecting too much, okay, so then it could be a problem, okay, and they could generate healthy issues and so on. So we are also trying to track feeding behavior and how the cows are behaving, and selecting feed. These will affect production. So putting all this together is the type of monitoring behavior that we are studying and trying to develop to be implemented in large scale operations. Okay. Other type of examples that we are doing in the lab is related to body weight. So the image that I showed you, the videos, they are from RGB cameras that generate to regular image, the same that you have in the phone. But we have at the farm 3D cameras that can give us depth image, and then we are using these to monitor growth development of animals, biometrics, and in adult animals, in the case of cows, we are using this to measure how much fat the cow is mobilizing, and based on that, if the cow is gonna get sick or not. So if the cow is mobilizing too much fat to supply energy to make milk, at some point the cow can get sick, and we don't want this to happen. So we want to use this as an early predictor of health issues, and then we're using those depth cameras. Okay. So in any computer vision system, the first step at the farm, if you want to do individualized analysis, is animal identification. First thing is identifying the cow, and then I can attach the phenotype. That could be body condition score, or the body weight, or the behavior measurement. I could say that cow is eating X meals per day. We're doing this through computer vision as well. So at the farm, we have 4 cameras installed at the exit of the milking parlor, and we can identify every single cow that is coming through with a reasonable accuracy. Okay, and that type of training is being done through CHTC, and I'll show more details about what we're doing with animal identification. The problem is with hosting cows, they have a black and white coat color. This is nice. It's like a unique QR code. You can use this to train the algorithm so the cow is recognized based on that pattern. As you move to large scale operation, the probability of having more cows that are all black or more cows that are all white, or if you have a breed like Jersey that are all brown, then it will be hard to identify cows using this. So what do? We have used 3D representations or 3D data and getting 3D representation as voxels and point clouds to classify animals, okay? So to do this, we have to train 3D convolutional neural networks, and those are neural networks that are heavy to train, and that's, again, why we need to use HTCondor to train that. One example that I got here is from Rafael. Rafael is a PhD student in the lab, and he deployed a puppy line of analysis from which we need to train several steps using HTCondor, and we have the summary of what we took to have that ready. So that system can generate infrared and depth image, those two images every time a single cow passes through, and you generate 10 frames, a sequence of 10 frames of each cow that is passing through the lane. So the first step that Rafael developed is to classify what is a good image and a bad image. So we have a deep learning classifying good image from bad image. So we only select an image that I have the entire cow below the camera. To do this, we have this type of network with 23 million parameters. And after this, after selecting the good image, we run another network, deep neural network, that do image segmentation. So we generate a mask of that. And having the mask, we apply this to the depth image, and now I can have the shape of the cow, and I can classify if the cow is too fatty or too skinny. Okay, we're using another network. And after giving the body condition score, I classify the identification. I give it the identification using another network. And if I don't have color, I use the 3D shape of the cow, and I classify which individual cow is that, and then I'm done. Okay. Now, to do this, only with 60 cows, what it took for us to have was 127 jobs, an average of 200K images per job, and a total time of 1,800 hours training. Rafael will always ask you one GPU, maybe something he could do differently, ask more GPUs to train, but that's what he did. And that's the total GPU memory usage. So clearly we could not have done this in our lab, okay? That's only one student. I have several other students doing similar analysis and with more cows and with more cameras, with more phenotypes, and running also inference. So that's a good illustration about how we are using HTCondor with animal identification and body condition of animals only. What about inference? Before going to HTCondor and asking, hey, Brian, let's try to do Christina inference in automated and real-time way, we developed a prototype in Azure just to see how this would behave. And we have run 104K image, considering a farm sending data every day, and running this pipeline of selecting good images, segmenting, identify cows. The total execution time was 60,000 hours. And this is because it's not inference only, but it's the whole pipeline of data transfer in the cloud, which we need to get image, raw image, and crop the image, generate mask, and save in another blob, and generate the image for identification, save in another. So it's a lot of data transfer, not only inference. And for each process, for each task, we write something in the SQL to coordinate and to know what is happening in terms of log. And some of the tasks only happen after checking the SQL database. So that's why it's much longer than the training time. But we developed this, so we have that inference automated. We do not have the total memory that was used, but we have the total memory allocated per instance. And in this case, we're only using 200 max parallel instance. So that's what we can process at the same time. That's something we'd love to do using HTCondor. It's something that uses only CPUs, and expanding this for commercial farms and doing this in more large scales, we definitely would like to see how we can transfer that data and make inference using the infrastructure that I have here in campus. This is a done deal for those networks. We train once and it's trained. We don't have to retrain again. For animal identification, it's a problem. Here, we don't have a done deal. We have animals, new animals coming the farm every day, new animals coming into the milking system. And this is an open set problem. So we need to retrain, we need to retrain daily or maybe weekly. So I have a classifier with the new cows that are coming. To do this, we would need approximately 10 hours using one GPU based on what we're doing now. If you have more GPUs available, we could decrease training time, so we could train every night possibly. But then going to a farm with more animals, this would also increase. The computational resource would significantly increase. So what we are developing at the UW, we have 40 RGB cameras generating data every 5 seconds, depth cameras collecting image for every single cow. Compared to other domains, we do not generate large data sets, but in our domain, this is hard to handle. In the animal science department, we have data storage, we are storing data because we have the vision that this will create some really important computer vision system thinking about livestock and possibly in the future, a larger public database which people could benefit or have image, audio, and other type of sensing technology. So we have that set up, and that's how our lab that we are working now, but we are trying to expand, and we are having great support from CHC, specifically from Brian Miron, that are always supportive of this idea related to computer vision livestock. Some of the challenges talking with the guys in our lab, one of the biggest challenges, probably the major one, is the transfer of database, large database every time you need to train a job. So we have hundreds and thousands of images. So every time we need to train, we need to put that in stage. So that's probably one of the bottlenecks that we have is the data transfer, at least talking to them. That's some of the challenge that we have with this size of data set that we are working now. They mentioned also number of GPU for concurrent jobs. Sometimes it's a little limited, but I don't think that's a major problem. Probably the transfer of large database is something that we see as every time that we need to transfer 200,000 images, it's always a lot. One thing that I just want to bring is I teach a course, digital agriculture. The students use GPUs. They have a graphical interface, so I assign a virtual machines with they can use Linux or Windows, and they train the image and they work with image analysis. And it would be nice in the future if we could have some sort of interface with HTCondor, so then I don't have to use cloud computing in the teaching aspect. So it's something that I know it's not part of the real challenge now, but it's something that I think it would be really nice. And for sure, there is no doubt that this is allowing us to have amazing computer vision system being developed for livestock operation. Very few groups in the world are doing this. We are ahead and doing things that no one is doing because of the size of the data set we are collecting and the capacity that we have to analyze this. The possibility of running concurrent jobs and testing different experiments at the same time. This is incredibly amazing, and this gives us a huge advantage. The collaboration with the folks at CHC, the support from Christina, Lauren, Brian Balkenman, Miron, these give us also a lot of advantage compared to other groups, and for sure give us very good papers and publications with realistic research in terms of large data sets that very few people have in their hands in livestock systems, okay? We have more people working in the group. I use Rafael as an example. They are also meeting jobs and working closely with you. And I have to thank them too. And thank you all the support, the funding agents that we have, and specifically again, the CHC, Christina, Lauren, Brian Balkenman, Miron. Thank you very much for all the support that you are giving to our lab and to our research.